All right, guys, Professor Burns here. We're going to start Unit 3 by looking at Section 4.1. And this whole unit is about derivatives and applications of derivatives. So we've learned now the techniques for finding a derivative. Now we're going to try to put some of this stuff into use. So make sure your phone is put away and turned off so it's not a distraction. I've got several definitions here that I'm going to give you that you're going to want to make sure you commit to memory. So follow along and take good notes here as we go through this section. We're starting off talking about extrema. That's a funny word, but it basically just is a plural word for extreme. Instead of saying extremes, we say extrema. Extrema on a closed interval, we would call absolute extrema. And this definition looks very formal, but we'll break it down. It says, let f be a function defined on a closed interval I. So I is the interval. So the interval might be from A to B, for example, is what they mean. And it contains C. So C is the x value inside this interval. F of C is an absolute minimum of the function in the interval if this is true. If f of c is less than or equal to or below everything else in that interval. That's what we mean. So if f of c, here's the example I've got in this picture. The minimum, this point right here is the minimum on this closed interval because it is the lowest in terms of the y values. It's the lowest in that closed interval. Likewise, f of c is an absolute maximum in the interval if the opposite is true, if f of c is greater than all the other values in that given interval. Collectively, we call these absolute extrema. So in this interval, you can see we've got a closed interval from -1 to 2. The maximum, the absolute maximum, occurred at the right endpoint because it was bigger, it was higher on the graph than every other y value in that interval. And the minimum, the absolute minimum, occurred inside the interval, and it just depends on the function. Absolute maximum and absolute minimum, they can occur either inside the function or they can occur at the endpoints. But basically, it's the highest and the lowest point on the graph. That's what we mean by absolute extrema. On the other hand, if we're talking about an open interval, then we may or may not have a maximum or minimum. So for example, in this picture, notice we have an open interval from -1 to 2 because we have holes at the end point. So there's still a minimum right here, but there's no maximum because where would the graph end? You can't really say. That point is no longer included on the graph. And where does it really end? There's no way to say. So there is no maximum in this picture. In this picture, we have an open interval again because it's not closed. We don't have a closed interval. It's got to be closed and continuous. And you can see the opposite is true. We have a maximum at that right endpoint, but we have no minimum because where that minimum was, they've put a hole there now. They've redefined it up here, but where is the minimum? You can't really answer that question. So in order for you to have an absolute maximum and a minimum, you have to have a closed interval and it has to be continuous. So that leads us to this very important theorem. It's called the extreme value theorem. And it says as long as you have a continuous function, that's the only requirement, it's a continuous function and it's a closed interval from A to B, then there has to be both a maximum and a minimum. There has to be a high and a low somewhere in that interval. And that's what we saw in this first picture. So that's the extreme value theorem tells us. There has to be a max, has to be a minimum, as long as we have a continuous function on a closed interval. Now, a next definition we're going to look at is the definition of local extrema. Local extrema, sometimes these are called relative extremas also, so make that note. Our textbook uses the term local. I sometimes say relative because that's how I first learned it. So if you hear me slip up and say that, that's what I mean. But I'll try to stick to the word local. If you have an open interval containing C, on which f of c is a maximum, then f of c is called a local maximum for f. If you have an open interval containing c where f of c is a minimum, then f of c is called a local minimum. All right, now what is the difference? Well, all these really are your peaks and your valleys in the graph. These are really your turning points is really what these are in the graph. So if you have an open interval and you've got a peak in the graph, that is a local maximum. If you've got an open interval and you've got a valley or a dip in the graph, that's going to be your local minimum. And what I want you to pay attention to is what is the derivative at these locations. Well, at the first one where they've labeled it hill here at 0, 0, notice that the tangent line would be the x-axis here, but the tangent line would be horizontal. Likewise, at the valley over here, the tangent line, if I drew it, would also be horizontal. So what is the slope of a horizontal line? Well, that would be 0, right? So the slope for both of these would be 0. So the derivative at these turning points is 0. And that's very, very important part of the definition that leads us to something called a critical number. So a critical number is when the first derivative, f prime of c, either equals 0 or does not exist. So a critical number is where the first derivative equals 0 or does not exist. Then c is called a critical number. Here, let me write this a little bit neater for us here. C is called a critical number for that function, and the critical number refers to the x value where that occurs. I'm calling it c, but that's your x value, your independent variable. So if f prime of c equals 0 or does not exist, then we have a critical number at that location. It says not all critical numbers are relative extrema. So not all critical numbers will give you this peak or this valley in the graph. But if you do have a relative extrema, it has to occur at a critical number. And I just noticed I already messed up. I used the term relative. This should say local. So I'll change that in your notes. So I think I've fixed that. By the time you've got this, it should say local. But remember, I use those words interchangeably. We'll talk more about local extrema later on. Right now, I want you to focus on the definition of critical number and how we find absolute extrema. So when you hear the word absolute, you want to think closed interval. That's the most important part here. So to find absolute extrema, we're looking at a closed interval. Absolute extrema are going to occur at either, so absolute extrema occur at either the critical numbers, so either critical numbers or at the endpoints. That's where absolute maxima and minima are going to happen. And so when you're asked to find absolute max and minima, the first thing you're going to do is find the critical numbers for that particular function. So to find critical numbers, we're going to find the first derivative. So in this example, that would be 12x to the third minus 12x squared. And then we're going to set that equal to 0. If it is undefined, it would happen because we have a denominator. So there would be a situation where your first derivative has a denominator. If there's no denominator, you really don't have to worry about it. This is a polynomial. Polynomials are smooth, well-behaved functions. So they are always going to be defined. So you don't have to worry about that. But it is going to equal 0. How do we solve this equation? We're going to factor out a GCF of 12x squared, and that leaves me with x minus 1. And so then I'm going to use the zero product property, of course, to set both of those expressions equal to 0. I'm going to solve. I get x equals 0 and x equals 1. So this particular function has two critical numbers at 0 and 1. Now, how do we determine the absolute maximum and the absolute minimum? Well, remember what they were. They were literally just the highest and the lowest point in the graph. So the easiest way to figure these out is to just find where the highest and the lowest points are in the graph on that given interval. Remember what we're doing, absolute extrema. And I'm just going to take it, like I said, if they're going to occur, it's going to either be at the critical numbers or at the endpoints. So those are the only locations I need to check. I'm going to start with the left endpoint at -1. So I'll make sort of a little chart here on my paper. X equals -1. X equals 0 is the next number I come to. And then X equals 1. Those are my critical numbers. And then finally, the right endpoint is at X equals 2. If by chance you get a critical number that is outside the interval, you can ignore it. You don't have to worry about it. But these were both in the interval, so I'm going to include both of these. And then you're going to find what the value of the original function is, not the derivative, the original function, because I want to know the highs and the lows for each of these locations. So I'm going to take these numbers, -1, I'm going to plug it into the original function using my calculator. For the first one, I'm getting a value of 7. For the second one, I'm going to plug in 0 into, again, the original function. This is where I'm plugging these into. That doesn't look very clean. Let me highlight that for you. I'm plugging these into the original function right here. Okay, just so you know where I'm getting these from. Plug 0 in for x into this function, and we get a value of 0. Then I'm going to plug in 1. So if I plug in 1 into the original function here, I get a value of -1. And then if I plug in 2 into this original function, f of 2 gives me a value of 16. So in this closed interval here, where is the absolute maximum and the absolute minimum? So the absolute minimum would occur where the smallest y value was, and that was here. So that would be at 1, -1. If I said, what is the absolute minimum value, you would tell me -1. Value would be the y value. The absolute maximum would be where the biggest value was, and that would be right here. So that would be at the ordered pair 2, 16. So this is the process we're going to use to find absolute extrema, and that's what we're going to look at in class tomorrow. So make sure you bring your notes with you, and I'll see you in class.